Welcome back to this course on nanostructured materials, synthesis, properties, self assembly and applications. Today, we are in the module 3, lecture 13, and we will be doing 2 lectures from today on nanocomposites. Nanocomposites lecture 1 starts today, and this is the 13th lecture of module 3. Now, nanocomposites, the term as you can understand is a composite which has a nano sized ingredient. So, for example, commonly composites are made up of 2 materials which are mixed and they are not forming a compound with a specific stoichiometry, but you can vary the stoichiometry of 2 components, 2 materials which are say immiscible in each other. So, you can have a mixture of say sodium chloride with titanium dioxide, and when you mix them together you get a composite. Now, if you have one of these materials is nano size, for example, nanoparticles of titanium dioxide mixed with sodium chloride will form a nanocomposite. Similarly, nanoparticles of titanium dioxide mixed with a polymer will also form a nanocomposite. So, nanocomposites as such, if you take an X-ray pattern, will not give you the X-ray pattern of a particular compound, but it may give you X-ray pattern of 2 or more compounds. So, that is what is a composite, and if one of the materials is a nanoparticle or a nanorod or a nanowire, then that will be this mixture of material is a nanocomposite. The 2 ingredients or 3 ingredients, all of them need not be nano sized. Even if one of the ingredients is of nano dimensions, then its mixture with another material which has say micron sized particles will still be called a nanocomposite. So, what are nanocomposites? As I first explained what are composites, what are nanocomposites are multi constituent materials. One of the phases has 1, 2 or 3 dimensions of less than 100 nanometers. That means, one of the ingredients is a nanomaterial. It may be a nanoparticle, it may be a nanowire, or it may be a nanoplate. So, the mixture of that nano sized particle with some other material which has got say micron sized particles, or which may be a polymer which may not be at all a crystalline material, will be called a nanocomposite. Now, why nanocomposites are important? Because it will have superior overall properties compared to the constituents. So, you have 2 constituents A and B, one is a nanoparticle and B can be a nanoparticle or not a nanoparticle. If you measure the property of A and say the property of B, then individually their properties have some values, but when you make the composite and you measure the same property, it may be electrical property, it may be magnetic property, or it may be an optical property. Any of the property of the composite is better than either the same property in A or B. Hence, such nanocomposites will be better and superior in their properties of their individual compared to their individual components. Hence, you are interested in nanocomposites. The ability to tailor properties, whether mechanical, electrical, thermal, optical, electrochemical or catalytic properties of the nanocomposite will differ markedly from the component materials. So, you will be having the ability to tailor properties, because adding A to B is in your hand. So, if you control the addition of A to B and the properties are changing, Hence, you can control or tailor make the properties as you choose. So, there is an ability to modify the properties by judicious choice of the amount of the two components A and B to give you the resulting property. So, in nature there are many nanocomposites available, which we see in our daily life, made in nature by natural phenomena. Example is like abalone shells. Abalone shells are like found in marine animals, those found in the sea, and you can see many of them have shells, and these shells are made up of a mixture of many times calcium carbonate and maybe a polymer, which may be a biopolymer, and this is a composite which has a nanostructure of say calcium carbonate, or it may be calcium phosphate along with a biopolymer, and these are known as abalone shells found in marine animals. Similarly, bones, which is there in all most of the vertebrates, these bones are made up of calcium apatite, and it has got other fibrous material, and this makes the composite. So, bone is a composite of calcium apatite and some polymer which is a biopolymer, and it can be a mixture of biopolymers, and so it is a natural composite. So, these are two examples we see. There are many other examples of nanocomposites in nature. Now, the difference from normal composites. So, there are conventional composite materials. How are nanocomposites different from other composite materials? The area of composite materials is a very old area in material science and in engineering, materials engineering, and has been studied for over 60-70 years and has given rise to large amount of engineering materials, especially for their strength and controlling their ductility and malleability, etc. So, composite materials are not new. So, how are these new nanocomposites different from the earlier known composite materials? Now, these nanocomposites have exceptionally high surface to volume ratio of the reinforcing phase, and or it has exceptionally high aspect ratio. So, because you are putting nanoparticles as one or both of the components, or more than two components if it is made up of three materials, the addition of any nanoparticle or a nanowire increases the surface to volume ratio. So, that is a difference from normal composites. The nanocomposites will have a higher surface to volume ratio. It may also have exceptionally high aspect ratio, especially if you take nanofibers or nanowires. Then the reinforcing material, that is one of the components which is the reinforcing material, which normally is the nanoparticle, can be made up of several particles, example minerals, sheets or clay stacks, or fibers like carbon nanotubes or electrospun fibers, and the area of the interface between the matrix. The matrix is the larger material, larger component. Normally, the matrix may be ceramic or it may be a polymer, and the reinforcement phase is normally the nanoparticle or a nano plate or a nanowire. So, the interface between the matrix and reinforcement phase is typically an order of magnitude greater than for conventional composite materials. So, this since the particle size is small, so the surface to volume ratio is high, and the area of the interface. So, the connectivity between the matrix and the added particles, which is being called the reinforcement phase, the area of the interface is an order higher in these nanocomposites compared to normal composites, which may have micron sized particles. The matrix material properties are significantly altered in the vicinity of the reinforcement. So, wherever the reinforced particles are present, around them, if you look at the region just around those particles, they will be modified to a large extent compared to the material, the matrix material much farther away from those nanoparticles or farther away from the reinforcement particles. The matrix material as mentioned will be significantly affected in regions where the nanoparticles are present. Small amount of nanoscale addition can have an observable effect on the macro scale properties of the composite. So, what it means is that if you add even a small amounts of nanoparticle as reinforcement materials, say you add some silica nanoparticles in a bulk or ceramic silica, then you can observe some changes which you can measure by microscopic measurements. So, you can measure say the yield strength or the thermal expansion or things like that, which you can measure in the macro scale, that means on dimensions which are of the size of say millimeters, centimeters, etcetera. And this property which is being changed due to the nanomaterial being added will be reflected in the macroscopic property on a large sample of say millimeter or centimeter size. So, this is typically a nanocomposite of particles which are nano dimensions. So, these are nanoparticles along with fibers. So, the matrix here is the fibers and the nanoparticles is the phase which we are calling as the reinforcement particles. So, together this nanocomposite is a nanoparticle reinforced matrix, and this is the fiber, and as you see in between you will have these nanoparticles which are reinforcing these fibers, and the strength of this composite is going to be enhanced because of the presence of these nanoparticles compared to a system where there are only the fibers and no nanoparticles. So, this enhancement in the property gives you the interest to study and investigate and design new nanocomposites. So, what are some of the applications of nanocomposites? So, here we have listed some 4 major applications for which nanocomposites have been used, and the first example is as electrode materials for lithium ion batteries. One of the most important areas of research and development and applications in industry for and also for domestic purposes is the development of batteries which have long shelf life, can be used for several hundreds or thousands of cycles, and such batteries are based on lithium ion intercalation and deintercalation, and the electrode materials for such lithium ion batteries are being developed based on nanocomposites. So, this is a major area of industrial scientific and industrial research where nanocomposites are being developed for electrodes. Then another area is where you are looking at microwave absorbing materials, magnetic microwave absorbing materials. Especially these materials are of use in the defense, in space, in communication systems, and so there is a large market, and industry is very important. These materials are very important for industrial applications. Then another area of research again related to energy, like the lithium ion batteries related to energy, and here solid oxide fuel cells is also related to energy, where you get clean energy. That means, there is no pollutant produced as a function of the energy being produced, unlike many thermal and other types of fuel energy generation. In fuel cells, you basically use hydrogen and oxygen at 2 electrodes and generate energy, and water, which is non-pollutant, is produced as a byproduct. And when you have solid oxide as the electrolyte, then it is called a solid oxide fuel cell. And many nanocomposites are being used as electrodes in these solid oxide fuel cells. A lot of applications exist in the aerospace and marine industry, and this is a area which has tremendous market, because the aerospace industry always used lot of composites, and now people are trying to make nanocomposites which would replace the composites being used in the aircraft industry. The aircrafts have to use properties like the same material should have high strength, but at the same time should be light. And similarly, when you need a material which has 2 or more properties, then composites are of great importance. And in this area, composites have been developed for a long time for aircraft parts, for aircraft wings, and now nanocomposites are being tried out in the applications in the aircraft industry. Similarly, for marine applications, many nanocomposites for making lightweight ships, for making nanocomposite coatings as anti-fouling agents, which can be painted on the outside of the surface of the ship, such that with long usage the skin is not fouled by marine organisms and salt water, etc. So, there is tremendous applications in aerospace and marine industry based on nanocomposites. So, if you emphasize on one of the applications, that is electrode materials for lithium ion batteries, and look for nanocomposites for acting as such electrode materials, then people have investigated carbon mixed with oxide particles. So, some metal oxide and carbon particles together people have studied as nanocomposites. So, people have made use of nanocarbons. So, it may be carbon nanotubes, or it can be fullerenes with some metal oxide, retaining the properties which you require for a good electrode material, like good conductivity and good recycling properties and low thermal expansion, etc. So, you design composites keeping in mind the application, and hence keeping in mind the properties that you need, and maybe 2 or 3 properties need to be optimized, and hence you mix components such that one component gives the conducting property, the other component may give the mechanical strength, and a third component may give the property of low thermal expansion. Similarly, you can have other properties which are interlinked, and you can get a resultant material by mixing 2 or 3 properties materials of different properties, such that the resultant material gives an outstanding combination of those 2 and 3 properties. So, you can have carbon based particles mixed with metal oxide particles to give you nanocomposites, or a polymer mixed with metal oxide nanoparticles will also give you nanocomposites. And you can have metal particles like copper nanoparticles cobalt nanoparticles, nickel nanoparticles mixed with metal oxide nanoparticles. That will also give you metal oxide, and many times such composites made of a metal oxide with a metal particle are called cermets, because the metal oxide is a ceramic which is a non-conducting material, high temperature refractory material, and that ceramic with a metal is typically will be called cermet. And of course, if one of them is nano size, then it will be a nano composite or a nano cermet. And these combinations have been used to act as cathode materials in lithium ion batteries. Similarly, silicon based, tin based and other transition metal based oxide nanocomposites have also been designed and developed and investigated as anode materials, and their efficiency as anode materials has been measured by making cells and studying the current as a function of the properties, as a function of the dopant, which is the nanoparticle. Now, you can also, so these are some of the applications of nanocomposites, which you can see in the aircraft industry, in the automobile industry and in the marine industry. So, we just discussed that you have lot of applications in the automobile, in all kinds of transportation industries, and in the aircraft, of course, the properties have to be different depending on your application. In an aircraft, lightweight is being lightweight is a major property for the nanocomposite. So, the material has to be lightweight. In an aircraft, in a motor car, the property that you need mostly is that you need a scratch resistant coating. So, that this the surface is coated with a nanocomposite suspension, which gives you a very good shine and also is scratch resistant, and it may also have properties like it mechanically of very high strength, and so you make a nanocomposite depending on the application. For the marine industry, the property again you need the material which has high strength, lightweight, if you are making the structure of the marine vessel with that nanocomposite. However, if you are using a coating on the surface, then you need a coating which has a property such that that material does not get does not allow the corrosion of the structural material and does not allow fouling of the ship or the marine vessel. So, there are different applications depending on the what is your target industry, whether it is the aircraft industry or whether it is the marine industry or whether it is the automobile industry. So, if you extend those arguments, if you want to make a lot of composites have been used in structural materials, for example, in bridges, on the decks which form in the bridge, and there can be retrofitting of bridge columns using composites, and various new types of bridge structures with modern composites have been developed, which are again very lightweight, but of immense mechanical strength, and then you can design bridges with new structures, new type of structures as shown here. So, why now we come kind of summarize that why we need nanocomposites, and as we discussed, because you need two or more properties in the same material. So, you need multifunctional materials. So, when you mix two materials, the two materials bring their own properties and the composite has two functions. So, it is a multifunction. If you bring together three materials and make a material out of it, then you get a multifunctional material with maybe three optimal properties. So, typically you can have particles where some of the you can have composites with particles such that one of the material forms the core, the other the shell, and however, you can also have composites where the particles are all separate, but compacted together. So, you need what when you use nanocomposites, the properties, one is that the properties of interest are there in your composite. Second, you need small filler size, because the surface to volume ratio is very high, and between the two particles acting as fillers you have small distances. So, you get a bulk interfacial material. So, you have small filler size, the mechanical properties increase. So, you increase the ductility with no decrease of strength, and you increase the scratch resistance, and these are mechanical properties one wants to enhance in a material for industrial applications or for construction materials. Then for optical materials, you can have light transmission which is particle size dependent. So, if you have a composite and you are adding some nanoparticle, you have a choice of adding 20 nanometer particle, 40 nanometer particle, and you can vary the size of particles. By varying the size of particles in that composite, you can vary the amount of light which is transmitted through the nanoparticle, and hence you can modulate the optical properties. So, this is another application why nanocomposites are useful, apart from that they are multifunctional materials. So, this is an example of nanoscale alumina, that means alumina in nano sized particles, and the matrix here is a protein gel. So, when you have nanoscale alumina particles in a protein gel, so you get a composite, and if you make it as a film, so you have a nano composite film. Now, this is a TEM picture where you can see the continuous material which is the protein gel, and you have these particles which are nanoscale alumina which is dispersed in the protein or which is gelatin here. So, the protein is gelatin, and these alumina Al2O3, the Al2O3 nanoparticles are being used as filler. So, this kind of a composite film has its own advantages. So, one of the advantage is the scratch depth, and that is in a gelatin film how much depth you can scratch, that will decrease when you add nanoscale alumina fillers. So, for the same amount of pressure you can reduce the amount of depth of the scratch in films with nano fillers. So, and if you have less of this scratch resistance, then if you compare with micron size alumina filler compared to nano sized alumina filler, you will find that the scratch resistance is larger in the nanoscale film which has nano sized alumina. If you use micron sized alumina, then you can go to larger depths with the same pressure. So, the scratch resistance is lower when you are using micron sized alumina, and that will give you low transparency of the films. So, when you have easy scratch resistance, that means the transparency of the film will be poor, and this is what is seen when you have micron sized alumina instead of nano sized alumina. So, coming to optical clarity. So, the optical clarity will be higher in composites which have nano filled particles, nanoparticles filled composite films, and this optical clarity, that means where the visible light scattering has to be avoided. So, wherever the scattering is less, that will give you more optical clarity, and the scattering is basically when you have a mismatch of the refractive index in the polymer, which is gelatin, and in the filler, and the filler here is the alumina particles. So, when the refractive index mismatch is lower, then you will have more optical clarity. So, this is one example how you can improve a property, and here it is the optical property of the film along with the scratch resistance of the film, which has been improved using alumina nanoparticles. So, this is the measurement to show that you have, this is the optical property. So, the transmittance and the transmittance, as you see here you have the black one is pure gelatin, and when you add nano alumina filled gelatin, it is nearly the same. So, there is hardly any reduction in the transmittance, whereas if you use micron sized films, then you have tremendous loss in transmittance. So, the optical clarity will reduce much more if you use micron sized alumina instead of nano alumina. And this is a diagram to show that visible light is being passed. So, in this nanoparticulate film, it allows visible radiation to go through, whereas the ultraviolet radiation is scattered back, which you want. So, in many applications you do not want the UV rays to be going through the film, and only the visible rays are going through. So, you can design a composite film based on nanoparticles, which has this property of allowing visible light, and so it is clear, optically clear or optically transparent for visible radiation, whereas it is optically opaque, or which means that it does not allow the UV radiation to pass through. This is the scratch resistance test. So, these are AFM, atomic force microscope pictures of a film on which there is a scratch, and this is a film with of pure gelatin. There is no nanoparticle on this film. Now, if you add some nanoparticles and then do a scratch test, you see the scratch now is less visible than in the film where there was no nanoparticle. So, if you increase the amount of nanoparticles in the film, then you see that you can hardly see any scratch on this film where the amount of nano alumina has been increased. So, there is no nano alumina, and here you add some nanoparticles, there are more nanoparticles, and the scratch resistance has increased dramatically as seen by this AFM pictures, and the surface roughness, which is a measure of the scratch resistance, the surface roughness will be very small in this case, because it is scratch resistant, and you can measure the surface roughness using atomic force microscope. Now, these are some experiments. You can also do modeling, theoretically or computational modeling and simulation of polymer based nanocomposites, where you have one of the components is a polymer to which you add some nanoparticles, and you can model and simulate what would be its properties, what will be the mechanical properties of a particular composite which has so much amount of nanoparticles in a matrix of a particular polymer. Now, this kind of computational modeling is of use when you want to design a new material for a particular or specific application. So, the scale here, what is shown here is to explain to you why people call this multi-scale modeling. It is called multi-scale modeling because the modeling takes into care small variation in properties due to small changes in distances which are at the nano regime. So, you are talking of nanoscale, where the distances are between two atoms in the sub nanoscales region, which is the atomic dimensions, and hence you see you are here it is the inter atomic distances which become important. And as you go to the 100 nanometer size, now you have got these fragments or oligomers of polymer, and you have nanoparticles of say 10, 20, 30 nanometers. So, these are atomic scale distances which are inbuilt in the particles which are of say 100 nanometers, along with some chains of polymers which are maybe few monomers. So, it may be oligomers, and then you go to larger scale. So, from smaller scale you are going to larger scale. So, you put many of these together and you are in a scale which is at a micron level. So, you are looking at 1000 nanometers, and then finally, you come to objects which we can see with our naked eye in the macro scale. So, something which we can see with our eyes like 1 centimeter long substance. So, this final layered composite, if you take a small region and look under the microscope, you will be seeing regions which are of the order of microns. If you take a small region in this micron sized object and you look deeper, then you see objects which are in the range of few 100 nanometers. And then if you go further down within the nanoparticles, you will see atomic distances. So, different length scales are involved. You have atomic length scales which are sub nanometer, you have nanometer sized length scales, you have micron sized length scales, and then you have hundreds or thousands of micron length scales which is visible to the naked eye. So, since so many length scales are involved in the same material, the same material which is the final product, a layered composite, can be understood at different length scales. Hence, it is called multi-scale modeling. So, all these different length scales are built when you try to understand theoretically or computationally the properties of a composite, especially polymer nanocomposites, where the matrix is a polymer and you have nanoparticles being embedded in that, which is acting as a filler. And then if you do a simulation at these length scales, then you do a multi-scale modeling and you can come up with some final properties which these polymer nanocomposites will have. This is an area which is of lot of interest in the current computational materials science. So, in multi-scale modeling and simulation, what we can do, what can be predicted if one does multi-scale modeling of polymer nanocomposites. So, you can try to understand the mobility after understanding the interactions between the particle and polymer. So, there are polymer chains and there are particles, and you try to understand the interaction. That means, you try to understand the mobility, the conformation of the polymer chains, the crystallinity, and how do you control the chemistry to control the conformation and crystallinity. So, this can be predicted. If we can predict this, then we can design and control these nanocomposites. So, we have to predict these interactions using multi-scale modeling and simulation. Apart from polymer particle interaction, particle particle interaction has to be understood. So, there what people do is what is called a coarse grain theory, where you go from mesoscale to the continuum, and then the effect of these interactions and particle size on the local and global properties, that is the such as mechanical properties, thermal, electrical and optical properties should be predicted. And so, one goes from the coarse grain theory to the multi-scale continuum, and then once you know you are able to predict these, then you can design and control the composite by the extent of the interaction zone, the polymer mobility, the particle dispersion state, the transparency, the structure of the defects, the glass transition temperature, which is the temperature at which you have a glass amorphous solid, which a polymer behaves like an amorphous solid, has a transition temperature which is called the glass transition temperature, and it is very important to understand the glass transition temperature to understand many of these properties of these polymers. And if you can predict all these things, then you can optimize the processing conditions and you can optimize the various properties or functions of these nano composites or polymer based nano composites. Now, that was multi-scale modeling of polymer nanocomposites. Now, why are people interested in polymer nanocomposites? One of the major areas for the interest on polymer nanocomposites is in the area of biomedical engineering. So, applications in biomedical engineering or biomedical science, for example, you can design and synthesize bio nanocomposites. So, what are bio nanocomposites? This is a class of hybrid materials, that means combination of materials derived from natural and synthetic biodegradable polymers and organic or inorganic fillers. So, you can have a natural or man made, that is laboratory synthesized polymer which is biodegradable, because ultimately you want, today one wants biodegradable polymers, that means polymers which can be naturally degraded over time by appropriate bacteria, etc. So, you want biodegradable polymers, and you may be having some nanoparticles as fillers, they may be organic or inorganic, and these kind of bio nanocomposites are important in several biomedical applications. So, an example is hydroxyapatite polymer nanocomposites, which are used as a biocompatible and osteoconductive substitute for bone repair and implantation. So, this is a synthetic material, it is a substituent for bone, and so people use this combination of hydroxyapatite and polymer nanocomposite for bone repair and implantation. Now, there are certain drawbacks of this material, because hydroxyapatite is difficult to shape, that means difficult to make it in a particular shape, because it is very brittle, that means it breaks very easily. So, when you want to machine it to make it into a particular shape, because it has to fit into some part of the body, then it is very brittle and it is not very flexible. It also does not disperse very well and agglomerates. So, these hydroxyapatite powders, they can migrate from the site because of their ability to agglomerate, they can move from their site where it was implanted, and thus hydroxyapatite as such is not very efficient for the purpose for which it is planned, that is as a substituent for bone or bone either implantation or for bone repair. So, to overcome this, instead of using pure hydroxyapatite, you incorporate these hydroxyapatite in a polymer to make nanocomposites. So, people have tried various types of polymers, for example, polysaccharide and polypeptide matrices have been used with hydroxyapatite for composite formation. So, one of the polymers people have chosen biopolymers is chitosan, and chitosan with hydroxyapatite you get nanocomposites, and this nanocomposite has lot of important properties, very much useful for bone replacement, and that is one of the properties is it is highly flexible and has a high resistance on heating because of intramolecular hydrogen bonds formed between the hydroxyl groups of hydroxyapatite and amino groups in the chitosan, which is the biopolymer. And so, this kind of nanocomposite can be used as a substituent for bone. Now, this is a SEM picture of a polymer nanocomposite between hydroxyapatite and chitosan with a gelatin scaffold, and you see these kind of features. These features are around 500 micron or more, and it shows a very highly compacted structure, and this has applications in tissue engineering. So, there is a lot of work being done on polymer nanocomposites, especially for biomedical applications, and chitosan is a important biopolymer which is being used in the presence of hydroxyapatite for these applications. Now, people have also used other type of polymer nanocomposites, and in that shape memory composites are very important. Now, what is this shape memory polymer matrix? These are materials which can remember their or retain their shape after a mechanical strain has been removed. So, suppose you take an example where this material, this shape memory polymer matrix is heated. When it heats, when you heat, there is a large mechanical strain which develops, and this polymer nanocomposite may bend itself, and when you remove the strain, that means you cool the substance, it goes back to its original shape. So, it is as if the polymer remembers what was its original shape. It is a polymer nanocomposite, and hence it is called a shape memory polymer nanocomposite, because once you remove the external force or the external stimuli, in this case that is temperature, because you are applying heat, and due to that there is a development of a strain. You remove the heat and that strain goes back, and the structure changes to the original shape. Now, this can be used for MEMS devices, and what is MEMS? MEMS is micro electromechanical systems, and similarly today the next generation of MEMS is called NEMS, that is nano electromechanical systems. So, here this can be, this type of shape memory polymer nanocomposites can be used as actuators or actuation materials, where the application of a particular external stimuli changes the shape, and removal of that external stimuli brings it back to the original shape. And so, this kind of devices used in for in vivo functions, that is inside a living system, living cell, or is called biomems, because you are doing a application in biology or in life sciences, and this kind of shape memory polymer nanocomposite based biomems have been performed in vivo, and such as they can hold like gripping or releasing of medical devices within blood vessels. So, you make this to hold some vessels or within the blood vessels to hold some particular organelle, and then removing the external strain, it goes back and releases whatever it was holding. So, such biomems based devices have been used for gripping or releasing of medical devices. A medical device can be a small surgical implant, or it can be a drug, or it can be a capsule. So, depending on that, such kind of devices have been made in the area of biomems. So, this is the example shown here is basically of a polymer nanocomposite, where you have a shape memory polymer matrix which and a nanoparticle. In this particular case, it is silicon carbide nanoparticles, which is a high strength material, and this silicon carbide with this shape memory polymer forms a composite and shows a variation in its shape depending on temperature. Now, coming to different classes of nanocomposites, you can have ceramic matrix nanocomposites, where you have ceramic like oxide, nitride, chalcogenides. These are called ceramics. Mainly oxides, nitrides and fluorides are called ceramics, because they are stable at high temperatures. Normally, materials which are stable at high temperatures are called ceramics, especially those which are metal oxides or metal nitrides or metal fluorides. And so, if you have one material which is a ceramic with another nanoparticle, then it is called a ceramic matrix nanocomposite. However, if you have a nanoparticle which is, for example, a metal, so here you can have a ceramic which is a nanoparticle with a matrix which is, for example, a polymer or another bulk ceramic having micron sized particles, then that is a ceramic matrix nanocomposite. On the other hand, if you have nanoparticles of metals, say copper, silver, gold, etc., small particles of metal embedded in a matrix can again be a polymer or a ceramic, then that will be called a metal matrix nanocomposite. And similarly, if you have a polymer with some other matrix, then you can have what is called a polymer matrix nanocomposite. So, these are different types of nanocomposites. Now, ceramic matrix nanocomposites, where the main volume, that is the main the bulk of the sample or the material that you have made is ceramic like an oxide or a nitride or a boride or a silicide, basically materials which have high melting points, that is they are refractory materials. When the most of the bulk of that is this ceramic, and you have small amount of other nano dopant or nanoparticles, then those are called ceramic matrix nanocomposites. And these ceramic matrix nanocomposites typically can encompass metal nanoparticles. So, the metal nanoparticles is the second component, and that is embedded in this ceramic matrix. Now, if these nanocomposites can have different properties, and depending on whether you are looking at optical, electrical or magnetic properties or corrosion resistance, you can see that these combinations of metal and this ceramic enhances those properties which you are studying. So, it may be corrosion resistance or scratch resistance or optical efficiency, the intensity of some light which is being transmitted. There is always an enhancement of these properties when you optimally choose the metal nanoparticles with the right kind of matrix, which is a ceramic. So, an example of a ceramic metal composite is titanium dioxide and copper nanoparticles. So, titanium dioxide is the matrix here, it is the bulk phase here, and in that you have incorporated small amounts of copper nanoparticles. So, then that becomes a ceramic metal composite, nanocomposite, and this nanocomposite shows a very high mechanical hardness. It shows small coefficient of friction and a high resistance to corrosion. So, this is an example. Titanium dioxide is micron sized, forms the matrix, is the bulk component in which a small amount of copper nanoparticles is embedded, impregnated or dispersed, and this combination of copper nanoparticles with titanium dioxide gives rise to very important properties and enhanced properties like large mechanical hardness, small coefficient of friction and lot of high resistance to corrosion. Then you can have metal matrix composites, and they can be continuous and non-continuous. For example, you can have carbon nanotube metal matrix composites. So, you can have carbon nanotubes and in a metal matrix. So, the carbon nanotubes here is the dispersed phase. It is the phase which is in small amount and the metal is in the large amount. So, you can have carbon nanotube based metal matrix composites, or similarly you can have boron nitride nanoparticles in a metal, or you can have carbon nitride in a metal matrix, and this gives rise to very high tensile strength and electrical conductivity of the carbon nanotube materials. So, we have discussed many classes of nanocomposites, especially polymer nanocomposites, metal ceramic nanocomposites and various nanocomposites based on their properties and functions like mechanical strength, optical properties, magnetic properties, etc. So, today we conclude the lecture here, and we will have the second lecture of nanocomposites will be our next lecture, and that would be the last lecture of module 3. Thank you very much, and we look forward to meeting you again.